Okay, so welcome back to this next video in which we are discussing atherosclerosis. Okay, right, so we're currently in the process of discussing the structure of low-density lipoprotein molecules. Okay, so I've given the motivation for what lipoproteins do. They transport lipid molecules within the blood and deliver them to peripheral tissue, basically. Okay, so low-density lipoprotein delivers cholesterol to peripheral tissue. Okay, that's the main sort of lipid that this form of lipoprotein actually contains to deliver to peripheral tissues. Now, all peripheral tissues need cholesterol because it's an essential component of the cell membrane. Okay, so it's often given a very bad name in the media, cholesterol. It's painted as this awful, awful molecule, but actually it's an essential part of all cell membranes, and all cells need it. Okay, so low-density lipoprotein has this role of delivering cholesterol to peripheral tissues. However, if you have too high levels of LDL within your blood, then basically you've got too much of a good thing, basically, and it starts causing pathology, and it starts to play a role in the development of atherosclerosis, but we'll come to that later. Okay, for now, let's just discuss the structure of low-density lipoproteins. Okay, so let me draw a picture of what a low-density lipoprotein looks like. So basically, these things are spheres of lipids. Okay, so imagine a sphere. Now, the outer surface of the sphere, okay, so imagine just having the outer surface of the sphere, is made up of a structure known as the phospholipid monolayer. Okay, so basically, this is going to be made up of loads and loads of phospholipids. So this outer layer is called the phospholipid monolayer. So I want to discuss with you the structure of a phospholipid, okay? Because there are two different types of phospholipids. Okay, but they all share a common feature, basically. Okay, so this outer layer is going to be made up of phospholipids. Okay, so what is the characteristic feature that you have to have in order to be considered a phospholipid? Well, basically, in order to be considered a phospholipid, you have to have something called a phosphate group within your structure, which we'll come to, okay? And you also need to have at least one long-chain carboxylic acid within your structure. Okay, so we'll start off with what I mean by a long-chain carboxylic acid. Okay, so long-chain carboxylic acids would have once been called fatty acids by biochemists. In fact, they still often are called fatty acids. Okay, and what they are is carboxylic acid molecules which have a really long hydrophobic tail. So let me give you an example, okay, and I'll go over onto the other side to do this. So, a nice example is stearic acid, okay? And the proper name for stearic acid is octadecanoic acid. So stearic acid is the old name for it. The more correct name is octadecanoic acid. And although octadecanoic acid is a bit of more of a mouthful than stearic acid, it's a more useful name because this tells us exactly what we're dealing with, whereas stearic acid doesn't really tell you anything about the structure of this. Octadecanoic acid tells us that we are dealing with an 18-carbon carboxylic acid. So let me draw this here. So I'll start off with the carboxylic acid head here. So here's the carboxylic acid group. And then we need 17 more carbons. We've got our first carbon, okay? The other 17 carbons are just going to be completely saturated with hydrogens, okay? So 16 of these are going to be in methylene groups, okay? So here is a methylene group, and we're going to repeat that 16 times, okay, like so. So because I don't want to draw 16 methylene groups, there is this beautiful trick whereby you can just draw one methylene group, and then you can put brackets around this single methylene group and subscript the brackets with a 16 to mean repeat this methylene group 16 times, and then right on the end, after the 16th methylene group, you'll then have a methyl group. Okay, now that gets me out of having to do an awful lot of work in drawing out 16 methylene groups, basically. Okay, so let's just check that we've got this right. We've got 1 carbon here, we've got 16 here, and 1 here. That takes us up to overall 18. So we've overall got an 18 carbon carboxylic acid molecule, and everything's completely saturated here. So this all looks good. We've got octadecanoic acid. Okay, so this is an example of a long-chain carboxylic acid. We can see that it's got an extremely long chain. Okay, it is a carboxylic acid, and also we're extremely hydrophobic. This tail is extremely hydrophobic because it's extremely neutral. Because, as I say, carbon and hydrogen have roughly the same electronegativities. Okay, so none of these bonds are polar, and certainly a carbon-carbon bond isn't going to be polar because carbon will have exactly the same electronegativity as another carbon. The only glimpse of some polarity is this carboxylic acid group up here, but often this is going to be involved in an ester link, and therefore it's going to lose a good deal of its polarity because the main polar group is this alcohol group down here, and that's going to be involved in the ester link after that. Okay, right, so in order to be considered a phospholipid, all you actually have to have within your structure then is a long-chain carboxylic acid, okay, of which I've got an example here, and also something else called a phosphate group, and I might as well introduce you to the concept of a phosphate group now, okay? So, a phosphate group basically consists of a phosphorus atom at the centre, and this phosphorus atom is double bound to an oxygen, and then off its sides it has 2 alcohol groups coming off, like so, and then it also has a single bond to an oxygen, which has then acquired a final electron through ionic means, and therefore has a negative charge. Okay, so this is the structure of a phosphate group. So all you have to have in your structure to be considered a phospholipid is 1 long-chain carboxylic acid and a phosphate group, and then you are considered a phospholipid. So, I want to look at the main 2 examples of phospholipids which are found within human cell membranes. Okay, so let's talk then about firstly the phosphoglycerolipids. Okay, and when you think of a phospholipid, the thing you're probably thinking of is a phosphoglycerolipid. So you might have a picture in your head of what a phospholipid looks like, and you're probably thinking of a phosphoglycerolipid. But there are other structures that obey these 2 criteria. Okay, right. So let's start off with what a phosphoglycerolipid is. So, as the name implies, it involves glycerol within its structure. Okay, so all phosphoglycerolipids are based fundamentally on a molecule known as phosphatidic acid. Okay, so let's start off with what the structure of phosphatidic acid is. So basically we'll draw a little cartoon for this to keep things nice and simple, because if we try drawing the molecular formula, it just becomes a mess basically. So we'll draw cartoons to keep it simple. Okay, so we'll have these 2 tails here, which represent 2 long-chain carboxylic acids, so just really long fatty acids. And I should stress that stearic acid is kind of the archetypal example of a long-chain carboxylic acid, but it is by no means the only example. You've also got palmitic acid, oleic acid, the list goes on, linoleic acid, loads and loads of long-chain carboxylic acids. Okay, so there are many different carboxylic acids which have extremely long hydrophobic tails. Okay, right. So this doesn't mean stearic acid necessarily, it means any old long-chain carboxylic acid. Then you've got a glycerol molecule, and then you've got a phosphate group attached up here. So let me talk you through this structure now in more detail. So let's colour things in. So these 2 horizontal lines, which are now coloured in orange, as I've said, these represent the long-chain carboxylic acids, or fatty acids. Okay? Now, often people will call long-chain carboxylic acids fatty acids. And the nice thing about calling them fatty acids is that we can then just abbreviate them to Fa. So I probably will do that from now on. I'll just abbreviate in diagrams long-chain carboxylic acids to Fa for fatty acids. Okay, right. Then those two long-chain carboxylic acids have been esterified to the first and the second alcohol groups of this glycerol molecule, which is being represented as this vertical line that is now coloured in green. Okay, so the vertical line in green represents the glycerol molecule. Now, glycerol is the old biochemist's name for a molecule that, strictly speaking, should be called propane 1,2,3 trial. Okay, and again, although propane 1,2,3 trial is a much more mouthful of a name than is glycerol, it's a useful name because it tells us exactly what we're dealing with here. It tells us that we're dealing with a 3-carbon molecule where you have alcohol groups coming off the first, the second, and the third carbon of that molecule. Okay, and to the alcohol group coming off the first and the second carbon of the glycerol molecule, you have esterified long-chain carboxylic acids. And I'll stress again that this doesn't necessarily mean stearic acid. You can have any old long-chain carboxylic acid here, and then a different, potentially, long-chain carboxylic acid here from in the first one. So there is a great deal of variation here. There's a great scope for making different phosphatidic acid molecules. Okay, so that's an important point. There is not just one phosphatidic acid molecule because, you know, you can have different long-chain carboxylic acids here. Okay, right. And then, attached to the alcohol group of the third carbon, what you have in pink here is a phosphate group. So let me show you how you can attach a phosphate group onto an alcohol group of the glycerol molecule. Okay, but maybe firstly it would be a good idea for me to show you how you can attach a long-chain carboxylic acid to an alcohol group. Okay, so we'll go over esterification, and then that will pave the way for us to understand how phosphate groups can then be attached onto alcohol groups of the glycerol molecule. Okay, so let's take our long-chain carboxylic acid here. So here's our carboxylic acid group, and then I'll just put R there for an arbitrary tail, basically. Then we've got our alcohol group here, which can be on the glycerol molecule. And basically we now want to bind this carboxylic acid group to the alcohol group via an ester link. Okay, so the way that this is done is you take the alcohol group off the carboxylic acid group, you take the hydrogen off the alcohol group. Okay, you combine those two things together to make water. So you break this bond, bind the two together to make water, and then you bind the carbon of the long-chain carboxylic acid to the oxygen of the alcohol group. Okay, and this link that you get here between this carboxylic acid group carbon and the oxygen of the alcohol group is known as an ester link. Okay, so that's what is meant by an ester link. That's how these long-chain carboxylic acids have been linked onto the first and second alcohol groups of our glycerol molecule. Okay, so let's now talk about how the phosphate group has been linked onto the alcohol group of the third carbon of the glycerol molecule. Okay, so let us draw out our phosphate group again. So here we have the phosphorus atom double bound to an oxygen with these two alcohol groups coming off it, and then this oxygen that's singly bound and has acquired another electron via ionic means and therefore has a negative charge there. Okay, right. So let me highlight this structure here, this phosphorus atom with a double bond to an oxygen and then an alcohol group coming off it. What does that look awfully like? Parallel it to this structure here. It looks awfully like the carboxylic acid group. In fact, if we replace that phosphorus atom with a carbon atom, that will be a carboxylic acid group. Ignore the fact that, you know, we've got 5 bonds coming off this thing, which is absurd for carbon. But if you just consider the thing that I have outlined in purple here, that would be a carboxylic acid group. So basically, phosphate groups can actually interact with alcohol groups in a very similar way to how carboxylic acid groups can interact with alcohol groups. So basically what can happen is the alcohol group can come off the phosphate group, the hydrogen of the alcohol group can come off the alcohol group. Those two things can be combined together to make water, okay? And you can then link the phosphorus atom onto the oxygen atom of the alcohol group. And this now is a very similar sort of link to an ester link, and to show the parallels, basically, to highlight the parallels between an esterification and this other sort of reaction between a phosphate group and an alcohol group, we call this link a phosphoester link. Okay? So, when you esterify or phosphoesterify a phosphate group onto an alcohol group, that forms a phosphoester link. Okay, so this is how we have attached this phosphate group here onto the alcohol group of the third carbon of the glycerol molecule via this phosphoester link. Okay, right. So, what we can then do is we can attach this alcohol group here, okay, onto other structures as well. Okay, so I'd just like to draw your attention to this as well, because basically even once you've attached this phosphate group onto an alcohol group, okay, so let's say we've attached this phosphate group onto this alcohol group of the glycerol molecule, even once you've done that, look what you still have intact here. You still have a phosphorus atom double bound to an oxygen atom with an alcohol group coming off it, now circled in turquoise here. Okay, this is exactly the same as the one that we originally had in purple here. Okay, so you can still form another phosphoester link with another alcohol group. Okay, so even once you've got this phosphate group attached onto the glycerol molecule, it can still attach onto other alcohol molecules because it still has one of these intact carboxylic acid-like groups, basically. Okay, and that will become important in a moment. So, we now understand the structure of phosphatidic acid, and again I'll stress that there is not just one phosphatidic acid molecule. There are many, because these long-chain carboxylic acids that are in these positions here are not set in stone. Okay, so this is the structure of a phosphatidic acid molecule. You have two long-chain carboxylic acids, those aren't set in stone. You then have a glycerol molecule and then a phosphate group coming off. Now, let me just also mention the difference between phosphatidic acid and then also phosphatidate. Okay, so people will often talk more about phosphatidate than they will talk about phosphatidic acid. Okay, and this is the reason. So, why is phosphatidic acid an acid? Okay, well, we have linked this phosphate group onto the alcohol group of the third carbon of the glycerol molecule. And I'm sorry that I've kind of drawn this back to front. Really, this should be the alcohol group of the glycerol molecule. But never mind, I said it this way first time, so we'll use this one as the alcohol group of the third carbon of the glycerol molecule. Okay, so once you have esterified that phosphate group onto the alcohol group of the third carbon of the glycerol molecule, you still have this other alcohol group here intact. And basically, this is capable of losing its proton. Okay, so the oxygen can lose its proton and the proton can go into solution. So at the moment, we have this oxygen double bound to this hydrogen atom, but the bond's very polar. Okay, so if I expand this a little bit, this bond is very polar, and the electrons in it are towards the oxygen, basically. So what can happen is the nucleus of the hydrogen atom, which just consists of a proton, can fall off effectively. It can go into the cytoplasm, okay, or whatever fluid it's within. It can go into solution, and the electrons remain with the oxygen. Okay, so the oxygen will gain a negative charge then, but you have donated a proton away into solution. So that's why phosphatidic acid is an acid, because the definition of an acid molecule is a molecule which is capable of donating protons into solution. Okay, now what you have left once the phosphatidic acid molecule has donated its proton away into solution, well, once the proton's gone into the solution, you'll have an oxygen left here, which will have both the electron that it put into this covalent bond and the electron from the hydrogen atom. Okay, so it will have gained an electron and it will therefore end up with a negative charge. Okay, so this will get a negative charge, which means that this molecule now is absolutely not an acid anymore. So when you think about the molecule where you have the phosphorus atom with 2 oxygens now with negative charges, that is absolutely not an acid molecule anymore, because it can't donate any protons away into the solution. Instead, it's actually a base. Okay, because it can accept protons out of the solution, and that's the definition of a base. Now, this is a running theme for all acids. This isn't special for phosphatidic acid. Okay, basically, if you have any old acid, often denoted like so, okay, at the moment it's got its proton attached to it. Basically, when it dissociates from its proton, okay, so when it actually does what acids do, the thing that you've got left over is a base, basically. It can't donate protons away anymore. It can actually receive them back again. And it's called the conjugate base of the acid. Okay, so this is what phosphatidate, strictly speaking, is. Phosphatidate is the conjugate base of phosphatidic acid. So once this alcohol group has donated its proton away, the molecule that you've got left is considered a phosphatidate molecule. Okay, now under physiological pH, generally phosphatidic acid molecules do lose their protons, and therefore they mainly exist in the conjugate base form, i.e. they mainly exist as phosphatidate molecules rather than as phosphatidic acid molecules. Okay, right, so that's the difference between phosphatidic acid and phosphatidate, and that's why most people talk about phosphatidate as opposed to phosphatidic acid. Right, okay, so that's the prerequisite for discussing phosphoglycerolipids. Basically, all phosphoglycerolipids are derivatives of phosphatidic acid. Okay, so what you do is you start off with a phosphatidic acid molecule, and you can add on extra structures onto the phosphatidic acid molecule, and what you then end up with is a phosphoglycerolipid. Now, phosphatidic acid itself is considered a phosphoglycerolipid. It's kind of considered the core phosphoglycerolipid from which all the other phosphoglycerolipids are then derived, basically. And notice another thing, phosphatidic acid itself is a phospholipid, okay, because it's got a phosphate group, and it's also got a long-chain carboxylic acid within its structure, so it is a phospholipid itself. Okay, so let's now see how we can derive the other phosphoglycerolipids from phosphatidic acid. So basically, what you can do is you can attach onto this phosphate group of the phosphatidic acid molecule an additional group in exactly the way I told you could. I told you that the phosphate group, even once it had been involved in the phosphester link to the alcohol group that comes off the 3rd carbon of the glycerol molecule, that this still had this intact carboxylic acid like group here, which can be involved in a phosphester link to another alcohol group. Okay, so we can attach on further groups onto phosphatidic acid molecules, providing they have an alcohol group. And this is how we produce phosphoglycerolipids from phosphatidic acid. So let me give you an example of a phosphoglycerolipid. And to do this, all I need to tell you about is what structure we're going to add on to this phosphate group here. Okay? So we're going to talk about the example of something called phosphatidylcholine. Okay, now this is a running theme for the naming of all of the phosphoglycerolipids. They all have this prefix phosphatidyl. Okay, so this prefix here, you'll see this a lot if you look at the phosphoglycerolipids. Phosphatidyl just means that within your structure you have this phosphatidic acid structure here. Okay, so that's all this portion of the name refers to. It means you've got a phosphatidic acid molecule within your structure. And then the choline portion, refers to the group that you have then added onto the phosphate group's other alcohol group of the phosphatidic acid molecule. Okay, so basically to get phosphatidylcholine, all you have to do is link phosphatidic acid to a choline alcohol molecule via a phosphester link. Okay, so let me show you the structure of a choline alcohol molecule. Well, we know one of these structures it must have in. We know it must have a functional group that is an alcohol within it. Okay, now this molecule, this alcohol of choline, is actually the same choline that you have within the famous neurotransmitter acetylcholine. In acetylcholine, the alcohol group of choline has been esterified with acetic acid to produce you acetylcholine. Okay, so we just now want to see the alcohol on its own, so pure choline. So here's the alcohol group intact and pure, and now off that alcohol group you have an ethylene group, which just means two methylene groups joined together. Okay, like so. And then off the other side you then have a nitrogen atom, and this nitrogen atom has 3 methyl groups coming off it, like so. Okay, now some of you will notice that there's a problem there. Nitrogen doesn't like having 4 bonds. It should only have 3 bonds. Okay, the fact that it has 4 bonds means that into one of these bonds, nitrogen has put both of the electrons. Okay, so usually nitrogen has 3 bonds and then a lone pair of electrons. When it has 4 bonds, it must be that one of these bonds consists of those 2 electrons in the lone pair that are both coming from the nitrogen and which make up both of the electrons within the covalent bond. So let's say it was this bond here that was made on these dodgy terms, okay? And basically what's happened is the nitrogen has put in both electrons and the carbon has put in absolutely none. Now, the normal understanding of a covalent bond is that one electron belongs to the nitrogen and one belongs to the carbon. So effectively, the nitrogen has given away an electron to the carbon, and then the carbon has sort of said, right, now let's form a covalent bond with this electron that I've just nicked off you. Okay, so it's a very dodgy deal here. But what this overall means is that the nitrogen has lost an electron, okay, and therefore it has a positive charge on it. And you might say, well, the carbon has gained an electron, so surely it should have a negative charge on it. But when the carbon entered this sordid arrangement, it will have originally had a positive charge. So it will have come in having lost an electron, okay, irresponsibly. And now it's come in here, and it's nicked one of these electrons off the nitrogen. It itself has become neutral because it's gained another electron with a negative charge. And then it's deferred the positive charge onto the nitrogen. So the entire choline molecule does in fact have a positive charge here. Okay, right. So that's the structure of a choline alcohol molecule. Now, all we're then going to do is link this alcohol group onto this turquoise group that remains within that phosphate group of the phosphatidic acid molecule, and then we'll have phosphatidylcholine. Now, phosphatidylcholine is often abbreviated to PC for short. P for phosphatidyl and C for choline, and it's also got an old name, okay, so I should mention this old name. It's also called lecithin, and if you do study lipid metabolism, this name will pop up all over the place, lecithin. Okay, so you should know what that means. It just means phosphatidylcholine, phosphatidic acid linked via a phosphester link to a choline molecule. Okay, right, so the phosphoglycerate then are a good example of phospholipids. They all have long-chain carboxylic acids within their structure, and then they have this phosphate group. However, they are not the only example of phospholipids. There are other examples of phospholipids that are important biologically, okay? And these are known as sphingomyelins. And we'll discuss the structure of sphingomyelins and more generally sphingolipids in the next video.